But welcome to the first LEAP lecture in climate data science for the spring 2026 semester. Thank you folks in the room and online joining us. And we're so thrilled to welcome SAMORY KPOTUFE. He is a professor here at Columbia University. He comes to us with a computer science degree from UC San Diego. He was a researcher at the Max Planck Institute for Intelligent Systems. He has spent time as an assistant research professor at the Toyota Technological Institute in Chicago, as well as at Princeton University, and he joined Columbia in spring of 2019. And SAMORY works in statistical machine learning theory that aims to understand performance limits in various problems of modern interest. He deals with adaptivity and modern application constraints. So SAMORY, thank you so much for joining us today, and it's all yours.
Thank you. All right, so I hope everybody can hear me. So thank you for the introduction, and I have to say thanks to LEAP for all the support over the last couple of years. What I wanted to talk about today is sort of a core research direction of mine that has led to various applications within climate science. And so the title, I'll explain the title in a minute. Mixed sample SGD. SGD here stands for stochastic gradient descent. And stochastic gradient descent, for most people who have done machine learning or do machine learning, stochastic gradient descent is the go-to optimization procedure in machine learning. And I hope I hope most people here are familiar with that, and people online should be familiar with stochastic gradient descent. And so I won't spend so much time on what stochastic gradient descent is, even though that's the core of the problem. How do we do stochastic gradient descent in a mixed sample regime? And so I'll explain that more in a minute. And so this is joint work with postdocs of mine, Yuyang Deng, Mohamed Kalan, Ethan Neugut, over the years. And much of the underlying insights come from joint work I've done with Steve Haneke. One of my main line of work is so-called transfer learning, where we're just trying to understand what sort of information is in a distribution or in a data set about a different data set, about a different distribution. So that's the high level of it, and that's transfer learning. All right, so interrupt me anytime and ask questions. I don't know how people online get to ask questions, but somebody asked me, okay. All right, so here is the basic motivation, modern classification or regression. Often in modern classification or regression, we no longer use just training data that is perfect. We no longer use perfect training data for our application. Instead, we might gather data from other sources that are not exactly predictive for our problem, but that we believe is somewhat related. So we have tons of data augmentations that we do, and that's the main motivation. Rather than using as we are taught in usual statistics, rather than using training data from the same distribution as my target application, I use a mix of training data from my target, and also training data from other sources. I hope that's sort of clear. Here is the simple formalism. I'm going to mostly consider prediction problems. So in prediction problems, we predict y as a function of x. And my target application, let's say my target distribution is Q, and I want normally to train just on data from Q. I want to do well on Q. I want to train on data from Q, but I also have data from P, from some source distribution. And now I want to estimate an F theta of X that predicts Y, but that has low error on the Q, my target distribution. Fine. And we can see this problem almost in all applications. In particular, we'll be caring about this problem in climate science applications. Much of the talk would skip climate science in the beginning just to give intuition as to this problem, how we resolve it, how we solve it. And then towards the end, I'll talk more about climate science. I hope that's clear to everyone. And in particular, I put here especially challenging. There are new challenges. There are challenges that go beyond the basic setup that I'll spend most of my time on. The basic setup is that of classification or regression. And the setup of the type of problems we care about in climate science will turn out to be a bit more challenging than basic classification or regression. And I'll explain that in the end. I hope that's clear to everyone. All right. So what is supervised transfer learning? So supervised transfer learning is generally just a generic term that is used to say we want to transfer information from one data set to another. That's all. Supervised transfer learning says the following, that rather than just having source data, some related source data, we also have a bit of the target data to inform us. Fine. So I want to train F theta on mixed data from P and Q. P is the source, Q is the target, and I want to do well on Q. That's the basic problem. So a popular objective is the following. How do I train now, right? The usual training would be minimize R hat Q of theta. That's the usual training. R hat here stands for my empirical risk. Fine. I want to minimize R hat Q of theta. But here I have data from P. And so now I want to minimize some type of mixture between the two empirical risks. Fine, everyone? So I want to minimize some type of mixture between the two. And the usual way we minimize anything, I said it earlier, in machine learning is through SGD and its variant. Stochastic gradient descent. Stochastic gradient descent, for those, I'm sure everybody knows gradient descent. Stochastic gradient descent just says rather than computing the gradient fully, I just compute it partially. Fine. The gradient in particular here is a gradient on a risk. The risk is an average. And so I compute an unbiased estimator of the gradient. That's stochastic gradient. And one simple way to do the unbiased estimation of the gradient is to randomly pick a sample and compute the gradient of the loss on that sample. That's called stochastic gradient descent. Is that clear? So stochastic gradient descent in particular involves subsampling the data. At every step where I'm optimizing towards theta star, I subsample the data, compute an approximate gradient, and use the approximate gradient within my optimization procedure. All right. So of interest here is our statistical and computational considerations. Statistical considerations, I'll explain them in a second more. Statistical considerations, by that I just mean I want to do well on future data from Q, not just on my sample. I want to do well on future data from Q. Fine. So I want to do well with respect to the true risk on the Q, not the empirical risk, not the risk I'm computing on my empirical data. I want to do well with respect to the true risk on the Q. And then computational considerations, I want to optimize this thing fast. In modern applications, how much data do I have? I have thousands, millions of data points, and I want to optimize this fast. And also, an issue that's going to come up immediately is how do I choose this alpha? I'm going to mix between R hat P and R hat P and R hat Q. How do I choose this alpha? And the whole training procedure is going to involve not only the gradient steps, but also to the choice of alpha. Fine? And I want to do all these things fast. So there are statistical and computational considerations which call for a new variant of SGD. That's the goal of this whole thing. A new variant of SGD that takes into account the fact that I have a mix of two risks to optimize, not just one risk to optimize. So that's the motivation. I hope that's clear.
What's the limitation of applying SGD to this objective?
What is what?
Limitation.
I'll explain. I'm going to go in details about this statistical and computational constraints, and then you'll see exactly what the limitations are. Fine, everyone? All right, so statistical considerations. again, consider this general objective. I want to estimate some theta hat alpha that minimizes this mixture of empirical risks. I'm caring about this objective, the performance on the Q. It's the future performance on the Q. Notice that I don't have a hat here. It's the future performance that I'm caring about, the performance on future data, because it's prediction, right? I want to care about the error on future data. So that's what I mean by R hat Q. And I want to be able to achieve the best possible error over my parameter class. I want to achieve as close as possible to the best possible error over my parameter class in the future using this empirical risk. So the choice of alpha immediately is critical, right? And here is some simple cartoon. Imagine I'm doing linear regression, fine. And imagine that the P data is in red and the Q data is in blue here. Here is a situation where P is very close to Q. So maybe I should rely a lot on the P data. The whole assumption is this, is that the P data is my source data, it's my augmentation data, and I have a lot of it. The whole reason why we're augmenting is because we have a lot of this imperfect source data. Is that clear? However, we don't know how imperfect it is. That's the key point. We don't know how imperfect it is. The only thing we know about P is through the data set that we are observing. So here in this case, if I knew P was that close to Q, I will use large alpha. I just don't know this a priori. Fine? In this other situation, P is very far from Q. So I should not rely so much on P. I should use very small alpha. Clear, everybody, what the issue is, the statistical issue. I just don't know the right alpha a priori. All I know is the data set I'm observing. Fine. In particular, the right alpha, I'm just going to call it alpha star. The right alpha is going to depend on the underlying distributions, P and Q, and on how many samples I have. If I don't have enough samples, I might not be able to discover at all that P is far from Q or P is close to Q. That's the point. So alpha star depends on all these parameters in unclear ways. Fine. So that's the statistical issue. I need to try to do this minimization using some type of alpha star, which I don't know a priori. The computational considerations are the following. Because I don't know alpha star a priori, what do people do in practice? They are going to try to cross-validate for alpha. Fine. I'll try a lot of different types of alphas. So what does that involve? That involves, and that's the key point here, the key point in the computation here is a double for loop. A double for loop is something that if you're a software engineer, you want to avoid at all costs. It's expensive. Is that sort of clear? There is an inner for loop that is just doing the gradient descent. Fine. It's iterating over the parameters. And then there is another for loop that is iterating over the possible choices of alpha. That can become very expensive. And at the end, you have to compute some type of score to even pick the best alpha, which we don't even know how to compute that score. Is that clear? Because it will be an empirical score. Should I use an empirical score that uses the little bit of perfect data that I have? Or should I use the one that uses a lot of the imperfect data that I have? That's also unclear. Is that problem sort of clear here? And all this is expensive. Now I want to design a faster alternative. That's the goal. Now that's the goal of this mixed sample SGD idea. Can I design a faster alternative that does just one loop, runs through the data in one loop, and behaves as if I know the alpha star? Is that clear to everyone? I'll stop here for a second because this is the main point of this whole line of work. And by the way, it will become clear. that this question I'm putting in a very simple way. It's a trade-off between computation and statistics. I'm putting it in a very simple way, but the trade-off is super unclear, and that's the whole point of much of what we're doing in mixed data settings. Fine, everyone? All right. So to try to start answering this question, I need to focus on some particular setting to gain insight on the problem. So I'll focus on the linear regression setting to gain insight on the problem. And then much of the talk will be on the linear regression setting. And then at the end, I'll tell you how we then move on to classification from the linear regression setting and how we then apply it to even more complicated classification problems in climate science. Fine? So linear regression, y is some linear function of x plus noise. Even though I say linear regression here, linear regression stands for a lot of different approaches we have in machine learning. Fine. I just don't mean simple linear regression. Polynomial regression falls under this thing because you can just view it in its linear form. Regression over high dimension, over infinite dimensional Hilbert spaces. So function spaces also falls in here as long as you can view the function space through through a linear basis of the space. Is that clear? And so we have RFF here. It stands for random Fourier features. It's a common approach in machine learning. Or you can think of it as using a linear probe over a neural network. Clear, everyone? So I just use linear regression as a simple formalism for the problem that we can focus on. And here, the loss that we are caring about is the square loss. We're caring about this particular risk. Mu here stands for P or Q, right? The source distribution or the target distribution. And then mixed sample SGD is what we call the procedure because it's SGD. That is going to try to sample from, now you have a mix of samples to sample from either the source or the target. And the choice of alpha here just becomes the sampling rate. How much should I sample from the source? How much should I sample from the target? Clear, everybody? And the goal of mixed sample SGD is to automatically decide whether to sample more from the source or to sample more from the target. Fine? Does that sort of now answer a bit your questions, the goal and all that? Fine? All right. In particular, one thing we want to guarantee is no negative transfer. What is called negative transfer? Negative transfer means the following. Suppose that the source is very imperfect. It's very far from the target data. It's not predictive. We want to automatically detect that. That's a huge problem in transfer learning, in applications of transfer learning. We want to automatically detect that and start sampling a lot more from the target without knowing a priori that the source is far from the target. That's the key point. Fine? All right. So to achieve this goal, we need to understand first what alpha star means. What is alpha star? What is the optimal, theoretically, what is the theoretical optimal choice of alpha in this problem? So that's the first thing we need to understand before we can now talk about, okay, we can compete with this baseline, the baseline being the optimal choice of alpha. I'm not sure who is familiar with minimax theory, but in statistics, we write this as a minimax problem. The optimal choice is the choice that achieves this best possible rate. The best possible rate is written this way. It just says, if over all possible algorithms, the minimum over all possible algorithms of the worst case that can be achieved on any given pair of distributions. So a first thing for us is to understand this minimax rate. That's the optimal, that's the best rate possible for any algorithm. That's the way to view it. It's the best possible rate for any algorithm. Can we achieve the best possible rate for any algorithm. Is that clear? That's the optimal. That's a notion of optimal rate. Fine. So that's just a way to rewrite the question. I want an alpha star. I want to be able to say that this algorithm, the mixed sample SGD, always achieves a rate akin to that of the best possible algorithm over the family of problems. Okay, so very little time. I spent a lot of time explaining the problem. So, okay. So minimax lower bounds. So that's the first thing I'll try to explain, at least at a high level. And then the main intuition about alpha star. And then I'll try to tell you about the mixed sample SGD, some experimental validation of our of this result in this linear case, and then I'll explain the climate science problem. I want to spend at least 5 minutes on the climate science, so I might not go into full detail over this part, just give you the high-level intuition as to how we arrive at the solution. All right, minimax lower bound. So this is all the work that we've done together with Steve Haneke, a collaborator of mine. So recall the setting. We are in a linear setting. We are interested in this. It's called an excess risk over the target. Okay. Q is that target. I want to do well on this target problem. And this is my notion of performance. Fine. Theta hat is any algorithm that uses a mix of samples. The main result says the following, that the best possible risk achievable for this problem is of this form. It's the minimum of two different risks. It's essentially an interpolation between two different risks. This here, D over NQ. NQ is the number of samples I have from the target. NP is the number of samples I have from the source. D is the dimension of the problem. D over NQ is the best possible risk I can achieve if I use the target sample alone. Now, this here is the best possible risk I can achieve in terms of the quality of the source sample. Is that clear? It's the best possible risk I can achieve on the target in terms of the quality of the source distribution. What is involved here? First, this term is easy to understand. The first term is just the first term in here. Let's go in this order. Lambda max of sigma p minus 1 sigma q. What is sigma p minus 1 sigma q? These are the covariances of the respective distributions. Fine. And the covariances of the respective distribution are just telling us how much the marginal px is different from the marginal qx. Then we also care about how much the conditional y given x differs from p to q. And that's captured by this other term. Is that sort of clear?
Why doesn't the first component of the minimum depend on the noise of the Q distribution?
It depends on the noise. I'm just forgetting noise here because these are the most important terms. Fine. Okay. And the most important term here that I want to focus on is that discrepancy between P and Q. Is that clear? And I'm just explaining that the discrepancy can be thought about the discrepancy in the X distribution and the discrepancy in the Y given X distribution. In particular, this is just the error of the best regressor on the P, on the Q. The error on the Q of the best regressor on the P. And then the discrepancy between the moments of the two distributions. And you can show that no algorithm can achieve a better rate than this interpolation between two rates. Clear, everyone? Now, minimax rates are essentially lower bounds. They just say that no algorithm can achieve these rates. Now there is the question of, these are called minimax lower bounds. No algorithm can achieve these rates. Now the question is, can an algorithm achieve it? Is that clear? And what sort of information the algorithm needs to know in order to achieve the rate? So here, the typical result of the following form. Consider again this type of algorithm, theta hat alpha, which minimizes a mixture of the empirical risk. The result of the form, there exists an alpha, a choice of alpha for which the rate is achieved. The best possible rate is achieved. Fine. And the main question we're asking is, how do you choose such an alpha in practice? And efficiently. Is that clear, everyone? Fine. So theoretically, the rate can be achieved. Can we achieve it in practice with a practical procedure? That's the question being asked. Fine. And cross-validation, this is, since I don't have so much time, you can just think about cross-validation. It turns out that cross-validation cannot do it. Maybe I'll give you a high-level intuition. Suppose I cross-validate using the target data. Fine. The whole problem there is that the target data, I had very little of it. Does that make sense? And so I can only achieve as much as the target data. I can only achieve a rate commensurate with the size of the target data. And yet, I want to be able to achieve a rate that takes into account the large amount of source data I have. Fine. So cross-validating just on the target data does not help me. I can now decide, let me cross-validate on the source data. If the source data happens to be imperfect, then it doesn't help me either. That's the key problem here with the cross-validation. Make sense for everybody? All right, so how do we then pick this alpha star? So here is the quick intuition. Let's look again at this objective. I want to minimize this thing over, I want to minimize over theta, this mixture of rates. Fine. If I look at it, I can rewrite it equivalently as minimizing r hat p of theta plus lambda, plus some lambda r hat q of theta. All I'm saying is that the 1 minus alpha is a nuisance. Is that clear? Fine. It's just a simple a first simplification. And now, why did I do this simplification? It's just to notice that this here happens to just be the Lagrangian of a constraint optimization problem. Fine. It's the Lagrangian of a problem of this form, minimize r hat p, subject to r hat q less than some delta to be specified. Fine. We know that these are square losses, so this is a convex program. So we know that the solution theta star satisfies a saddle point equation. There is a lambda star, there is a theta star, saddle point of the Lagrangian, which are the solution to this max-min problem, max over lambda, min over theta of this problem here. Fine. This here is actually the Lagrangian of this problem.
In case where you have a lot of perfect data, doesn't the Lagrange multiplier have to tend to infinity in this formulation? Because you want to take minimize empirical loss with only the Q term.
Should the
lambda not tend to infinity? In which case you can have problem to have it as a saddle point. If
but don't it? We're only considering finite sample problems, right? We're only considering finite sample problems that don't have any issue with lambda equal to infinity or or any such thing.
It's purely non-informative.
Even if P is purely non-informative. Look at it this way. I can always normalize the whole thing back to 1. Right? I started off with a normalization. Alpha plus 1 minus alpha is 1. Then alpha plus 1 minus alpha is still 1, right? I'm saying here is the point I'm saying. I'm saying that the problem is equivalent to a problem where my weights are bounded. It's not an issue. Okay? We can take that offline. Okay? The problem remains equivalent to a problem where my weights are bounded. Fine. we are all infinite samples, we're not going to have any blow up. And the solution always exists and is always finite because we're just dealing with purely convex problems. Clear, everyone? So now suppose that theta star achieves the best possible rate. Suppose theta star achieves the best possible rate. That means that the theta star is the solution to this particular problem with the lambda star in there. This is all this saddle point argument is saying. That if I know lambda star, then I can just let theta star minimize this thing with the lambda star. Fine. So effectively, the optimal choice of alpha, I just reduce it to the optimal choice of lambda. With just this relation between alpha star and this lambda star. Now, all I'm going to do is go back to the min-max problem and try to solve the min-max problem now with an SGD. There is a caveat, however. The caveat is this. What should this delta be for the solution to achieve the min-max rate I had earlier? Is that clear, everyone? So hence, if there is a delta such that this original problem achieves the minimax rate, then my alpha star is really, the alpha star of this problem is really the alpha star I'm after in terms of statistical rates. All right, so it turns out that yes, you can just set the delta to this, to D over NQ, to order dimension over NQ. Back to a question about variance. I forgot who asked the question about variance. You need variance also in here. Okay, the variance of the noise also in here. So you need to set, you just need to set delta that way. And the theorem just says that if you set delta that way, then you achieve this minimax rate. Now, here is a point I wanted to make here. Notice that I talked about negative transfer earlier. This rate guarantees no negative transfer. Do you see that? It's the minimum between two rates. If I use the target data alone, I always achieve the rate D over NQ. Is that clear? If it turns out that the best I can do with the source data is worse than the best I can do with the target data, the algorithm still just achieve the best I can do with the target data alone. Is that sort of clear, the point being made there? It's the minimum of two rates. So it's never going to do worse than using the target data alone, even if the source data is very bad. All right, for the sake of time, I cannot go really over the proof idea, but the proof is not that complicated. It just relies, it's a geometric proof. It just relies on the fact that this constraint here is saying, what is the constraint saying? The constraint is saying essentially return, so minimize the source subject to never doing too bad under the target. The theta hat Q here is the solution of optimizing over the target alone. Fine? So it says don't do too much worse than the solution of optimizing over the target alone. Is that clear? So this is the constraint problem. Now this constraint problem, we're going to try to use it and develop an SGD for it. Fine, everyone? So the first point here is that there is a constraint problem that achieves the optimal rate. Now, the next point would be, can we find the saddle point of the Lagrangian of this constraint problem? So that's mixed sample SGD. That's the key idea of mixed sample SGD. So the point is we're just going to try to find a solution for max lambda, mean theta of this thing, and do it all in one pass so that we don't have the double for loop anymore. Fine. And the way to do it in one pass is simple. I have a minimization problem. I have a maximization problem. I do an SGD for the minimization problem. I do an SGD for the maximization problem, and I keep alternating between them. The effect of it is that I have this lambda t plus 1 that is effectively a sampling rate. If I normalize it, it's a sampling rate. Fine. And I just use this sampling rate to sample. I change the sampling rate every time to sample, to decide whether I sample from the source or I sample from the target. And this will automatically switch between sampling more from the target or sampling more from the source, depending on how well the objective is performing. Now, the main complication in this problem is that the original problem had this theta hat q, which is the optimal solution for using the target alone, which for the sake of time, we don't want to compute separately. We just compute it in parallel. And so the constraint, in fact, is a moving constraint set. As opposed to a fixed constraint set, we have a moving constraint set, and the analysis has to show that this algorithm can keep track of the moving constraint set. Is that clear to everyone? So the guarantees are that with high probability, the solution that we get, in fact, also achieves nearly the minimax rate. And the high level of the proof idea is we base it on classical saddle point analysis for convex programs. Fine. Let me step back for a second. There is the original problem, which is just statistical. We have to show that the original convex constraint program achieves the minimax rate. Fine. Then we have this approximation to it, which is this SGD approximation to this problem. And the approximation involves not only approximating the gradient, but also involves this moving target, the moving constraint. And the analysis has to show that the solution of this, the computational solution of this, is very close to the solution of the original constraint problem. Close enough that the risk at the end will be the same risk. The risk on the target at the end will be the same risk. So that's the high level of it. So here I'll just talk quickly about extensions to general settings. The setting I consider so far is just linear regression. Why linear regression? Because linear regression is well understood. We understand the object involved. We understand what the risk, the form of the risk and such things. But it's a specific choice of loss. Then the question here is, can we move to more general losses? It turns out that we can handle more general losses as long as they are convex losses and also well-behaved, where saddle points are well-behaved and such. Now, is that enough? So, 1 second. Is that enough? For certain classification problems, I'll talk about classification problems in climate science in a second. The loss we care about there is actually the 0-1 loss. It's a misclassification loss, right? It's not convex. Fine? And so what we have to do in those cases is use so-called surrogate losses, a loss that is convex that bounds my 0-1 loss. Okay? A big open problem is when we extend to general losses, we can give you an upper bound, but we do not know whether this is the minimax rate for the problem, whether the alpha star is achieving the best possible rate for the problem. For the square loss in linear classes, we know this. So that's a big open problem for general losses. All right, so experimental validation. Go ahead, please.
mentioned computational considerations. You will mention the conversion speed of the algorithm.
Very good question. I just skipped over it.
The same as the just SGD, no?
It's just the SGD convergence speed, which is about 1 over square root big T. How fast you converging is about 1 over square root big T. However, here we have to also see how large should big T be in terms of sample sizes, the actual sample sizes, before we achieve the rate of 1 over NQ, or the minimum rate. It's just more complicated to explain that part. That's why I skipped it. But it's just the usual 1 over square root big T convergence. However, it brings in some other questions, which let me see. So here other questions come in. You have this learning rate, eta t, the learning rate, gamma t. You have to choose them properly. And the right choice of these learning rates gets very complicated. In the paper, we put theoretical choices that allows us to achieve the rates, but we believe that those theoretical choices are very conservative.
It's supposed to be the same in the classical improvement for the
Sorry?
the rates for the Freeman variable and the dual variable, that's supposed to be the same.
In fact, they are not the same. They are not the same because the considerations are a bit different. They are the same in terms of time t. They are not the same in terms of the constant that need to go over it. And the reason why is because, for instance, for this part, the constant that need to go over it have to do with the gradients on the surface of the constraint sets, the gradient behavior on the surface of the constraint sets. And those are things that we have to pre-compute to throw in. Is that sort of clear? All right. Experimental validation. So some of the quick thing we wanted to see is that we do avoid negative transfer. So here, theta hat PQ, the blue line, is this algorithm, the SSGD. The red line is using the target data alone. The green line is using the target. The green is using the source alone. So we're comparing with what if I ignore the target, or what if I ignore the source? Fine. As the source is getting worse and worse, so here what we're doing is we're making the source worse and worse. We take the best vector in the source and make it far and farther and farther from the best vector in the target. Clear? And so you can see the source is getting worse and worse using the source alone. And in all cases, our procedure never does worse than using the target alone. So it's avoiding this negative transfer. Is that clear, everyone? And it's an interpolation between the two rates, so it's doing better than the minimum of the two. It's not always going to be, in practice, better than the minimum of the two. Why? Because the rate is up to constant. The theoretical guarantees are up to constant. Is that sort of clear? But in general, you can expect this type of behavior. Here is the same thing. We're making the source far and farther from the target. Recall there are two different ways of making the source far from the target. One is through the conditionals. One is through the marginals. And that's all we checking. So here is the time. We're just comparing against an algorithm that tries to cross-validate over the possible alphas. And just showing the behavior of the double for loop versus just a single pass through the whole problem. All right, so very little time to talk about climate science, but let me just tell you what the main difficulties are here when we try to apply to get to the climate science problem. It turns out that it's not just, hey, we take the algorithm off the shelf and we apply it. Does that make sense? Because the problem I just explained to you is quite different from the type of problems that we're going to care about in climate science. Number one, I showed you a regression problem. I want to move to classification. So the first thing is I use a convex surrogate for the loss. That's the first thing. But the main problem is a bit different. So let's consider rare event detection in climate science. This is the problem I've been looking at with respect to the LEAP project. This is the problem I've been looking at for the last couple of years with my postdocs. So rare event detection, all I mean is the following. Imagine that I'm in the, I used this in the Catskill retreat last time. Imagine that I'm in Catskills, New York, and I'm just trying to understand, is there going to be some rare weather events in the summer? Fine. And the X data, imagine, is just usual readings, temperature, humidity, things like that in different locations. Okay. Different locations from the Catskills, that will be my augmented or my augmented data. Catskill data is its own data, but data from the past, imagine. Is that sort of clear? A little bit what's happening. Here, rare event detection is a bit different from pure classification in a sense I'll give in a minute. But first, think about the way we try to do rare event detection is we have a sense, we want to have some data from normal behavior. Okay? Here, normal weather. Imagine that normal weather has a particular distribution. Abnormal weather has a different distribution of temperature, humidity, and such things. Clear, everyone? So the main issue here is that we have to deal with two different types of error in rare event detection. In classification, we deal with one type of error, just the misclassification error. Fine. Here I have two different types of error. That's the main issue. I have so-called false positives. So maybe this is the threshold I'm trying to detect between the normal distribution and the abnormal distribution. Here is a threshold. And I'm going to care about not having too high of a false positive while also minimizing the false negative. That rare event detection. Is that clear to everybody? While in normal classification, we don't treat the two errors any differently. We just look at misclassification error all together. In particular, people call this a Neyman-Pearson classification problem. And the classification problem becomes minimize false negative subject to false positive being very low. The alpha is a pre-specified parameter, maybe 5%. I want to make sure that I have a detector that has at most 5% false positives. Is that clear? And that's a different goal from I want a classifier that achieves accuracy 95%. Is that clear, everyone? Now, add to this now changes in data distribution. What we mean by changes in data distribution, now all of a sudden I don't just have data from my normal weather, data from abnormal weather, but I also have augmented data of some type. Maybe the augmentation is a change in the abnormal data distribution. It could also be a change in the normal data distribution, which makes the problem a bit more complicated. Now, all of a sudden, for SSGD, I'm not dealing with just two different data sets from which I'm trying to decide where to sample. I can have up to 4 different data sets, 2 representing source normal, target normal, source abnormal, target abnormal. Clear, everybody? And I have to make similar decisions now. So the way we proceeded was it took a few years. First, we just assumed that there is only change in the abnormal. So that's work with Mohamed Kalan, Ethan Neugut. And we didn't really have the MSSGD procedure at that time. We had a version of it that did not have good guarantees. But we used a version of it in this paper. Then, together with Yuyang Deng, we developed MSSGD with full guarantees, the full guarantees that I presented a second ago and disappeared at NeurIPS this past year. Then we started tackling the problem of what if we have a complete changes in distributions, in the normal distributions, in the abnormal distribution. And that's together with Mohamed Kalan again and Yu Yang Deng. It was sent to iClear. iClear decisions apparently are coming today. I don't know. So the question mark, is it going to be accepted? We don't know. We hope so. And then here we implemented a full new MSSGD for this mix of 4 distributions. The key intuition is, again, the Lagrangian intuition I gave earlier, where we recast the problem as now a problem on multiple constraints. Is that clear, everyone? And the multiple constraints are natural here. There is a constraint just coming from the trying to lower false positives. And now there are also constraints coming from the changes in distribution. And we pull all that together, and we have similar guarantees that we can achieve optimal rates for this problem. So some quick evaluation, similar results. The black line here is the procedure, and the other lines are a lot of different baselines that we looked at for this problem. Outlier detection or novelty detection does not apply just to climate science. It also applies to other problems. So we also looked at many other problems, including problems in finance and similar behavior for the procedures. So I'll stop there. So the quick summary is this, is that we developed this efficient SGD procedure that adapts sampling to unknown shift in data distribution. It does not know the shift in data distribution a priori, but it can adapt the sampling over time to this unknown shift by relying on optimization theory. Initial experiments are promising. Back to one of your questions, the step sizes are something that we need to work on more better, because they are very conservative here, and how to automatically choose them in a non-conservative way. What I mean by that is this: we have the theoretical step sizes. That's what I'm showing. That's essentially what I'm showing. But when we try to play with the step sizes, we realize that we can even do better, but we don't have theory for that. That's the key point I'm making. Noise. You keep asking about noise. I was hiding the noise issue. We have to assume so far that we know the noise, the label noise. What we do to not assume it too much is we estimate the label noise and plug that in. The hope for us is that we have a better estimator of the label noise, or we need to truly understand the effect of the noise in this whole procedure. If the noise is bounded, the results remain the same, but you can have uncharacteristic label noise in a lot of applications. The multi-source case is completely open. A lot of this assumes that you have a finite number, a small number of augmentations, of augmented distributions. The case where you have a lot of them becomes very complicated, because now all of a sudden you have very complicated mixtures that might be optimal. Is that clear a bit? And so we do not know how to handle the general case, and that's the main open problem we want to work on now. So, all right, thank you. That's all.
Are there any questions in the room?
I have one question.
Please.
On that, we usually also use transfer learning to research. So I have a question on, like, a lot of people, even in the industry, also use transfer learning for seeing if it helps them to reduce the computational cost of doing, like, it's not only on the optimization, but also on the computational resources that they would have spent otherwise without using transfer learning. So have you seen?
I've never seen that.
Okay.
Because for me, transfer learning is about statistics. It's about improving my statistical performance.
Okay.
But I've never seen that. That's interesting. I'll ask you more about it. But I've never seen trying to use additional data to improve computational cost, I've never seen. And it's counterintuitive to me.
Yeah. Okay. Sure.
Okay.
Are there any other questions in the room? If you have questions on Zoom, please feel free to unmute yourself and ask SAMORY. Hold on one second.
Yeah, thanks for the very clear presentation. Is there a case in this literature where you want to mix, so not only P and Q are different, but the losses that you try to mix are different?
Very good question. That's very open.
That's open. Okay.
Yeah. And in fact, the losses that you care about are always, when you're in classification, I'm using surrogate losses. The losses are different from the eventual classification loss, but there is no theory on that.
Okay.
Does that make sense? There is very little theory, even outside of transfer learning, on surrogate losses. We do only understand some cases where surrogate losses, theoretically, where surrogate losses are fine. But surrogate losses can hurt you also. And that's not fully understood either. Is that clear?
Okay, if there are no further questions, SAMORY, thank you for kicking off our spring semester.
All right. Thank you. Thanks a lot, everyone.